why in the world do we factor? What is the point? Why do we care? Why is this something that we would ever want to do? Like take an expression like the one I have up here on the board, x squared minus 3x minus 18. What good does it do to factor? Well, if you can't defend factoring, if you can't defend why we're learning how to factor in the first place, it means that you're missing exactly the point that I want us not to miss, right? And I see it happen in this class regularly, every semester, that you can pick up how to factor. You can pick up all the tools and the tricks and everything, but then when the chips are down and when factoring is most useful to do in another problem, in a problem that's not saying, please factor this, right? In a problem in which you're doing something else and in which factoring is a useful tool, maybe an essential tool, people forget that it's a thing. They forget how to use it because we don't know why it's useful, why it's important. So what I want to do with us today is to take this factoring problem and to look at it, as we did on Monday, from two different perspectives. On Monday, remember, we talked about greatest common divisor factoring. And the first question we had was to find the greatest common divisor of a couple of monomial expressions. And then the piggyback to that was use that answer to do something else. Use that answer to factor a binomial. So I want to do that again here. So I want us to factor this expression. It's quadratic with leading coefficient 1, but whatever. It's an expression. We'll factor it. But then to piggyback on that, here's the second task. And this second task is going to help me to motivate why we care about factoring in the first place. So factoring is something we do to expressions, right? This is an expression over here on the left. It's just a combination of numbers and variables, but has a numerical value, but it doesn't have a truth value. It can't be a true expression or a false expression. It has a value, a number attached to it. But factoring is useful because it doesn't just help us with expressions, it helps us with equations. And so here's my point. Factoring the expression x squared minus 3x minus 18 can actually help us to solve an equation that has that expression in it. And so what I'd like for you to do after you've factored the expression on the left is to try and use that answer, your factorization that you find in the first part of this problem, and use it to help you with the question of solving the equation that has that expression on one side and has a 0 on the other. In the question that asks you to solve the equation x squared minus 3x minus 18 equals 0 for x, what solution or solutions did you get? I'll get a couple people to volunteer their answer. So what did you get for x in that equation? So first thing to notice is that this equation, if you believe Darren's answer, and I do, our job, I think, is to convince you to believe it as well. But if you believe that answer, this is the first time we've seen an equation that has more than one possible solution. Right? The whole first half of the course, when we solved equations, we got equations that only had one answer, with the exception of some time in Module 3 when we were working with absolute value equations. Absolute value equations had, in general, they could have two solutions. This equation doesn't have an absolute value, but it does have two solutions. So let me quickly ask you, what is it about this equation that makes it possible for there to be two solutions? What's our cue that can tell us that an equation like this one might have two solutions? Up front, what is it about this equation? This is the point that's so important in algebra that it actually goes by the name the fundamental theorem of algebra. And when a mathematician calls something a fundamental theorem, you can bet that it's pretty important. The fundamental theorem of algebra tells us that an equation can have as many solutions as the degree of the equation, which means the highest exponent on the polynomial which is on the other side of the equation from 0. So fundamental theorem of algebra tells us that we may have as many as two solutions to this particular equation, and that 2 corresponds with this 2, the highest power of x that resides in our polynomial. Up to 2 solutions. And if we believe Darren's answer, and I do, this equation actually does have 2 solutions. So let's figure out how we got there, because I saw a few of you were able to tackle the left-hand problem, but didn't quite make the connection to the problem on the right. But that's good. That's why we're having this conversation, so that we can make that connection. So let's go back to the beginning, to the first task on this problem, which was just to factor the expression x squared minus 3x minus 18. What approach did you use to factor this expression? according to our general strategy for factoring that we talked about on Monday, the first step is always to see, is there a GCF? Is there a greatest common factor that we can factor out of every term in our expression? So what is the GCF of these three terms, x squared, 3x, and 18? What coefficient is really in front of this x squared right here, secretly? A 1. And so as soon as we have a 1 as one of our three things that we're trying to find a greatest common factor of, the only factors that 1 has are 1. And so that we can't have anything which is a greater common factor of the three numbers in this problem besides 1. And 1 isn't interesting as a factor. It doesn't help us to get anywhere, because dividing by 1, multiplying by 1, doesn't actually do anything to an expression. How about the powers of x? How many powers of x do these three terms have in common? So both of our first two terms have at least one power of x in them in common, but the third one doesn't. Right? So there's no number of powers of x that can be a part of our greatest common factor either. Right? X to the power 0. And x to the power 0 is just 1. So even though we should always start with the greatest common factor in our general factoring strategy, there are examples like this one where it doesn't actually do anything for us. Right? So we found out the greatest common factor is 1, and factoring out 1 doesn't actually help us. Right? It would just look like this is equal to 1 times x squared minus 3x minus 18. And we're still left with the task of factoring the x squared minus 3x minus 18. But at least now we know that we can't get anywhere with the GCF, and we have to do something else. So what was the next step from here? Now that we know the GCF isn't going to get us to where we need to go, what other options do we have? To factor a trinomial like x squared minus 3x minus 18 is you go looking for a pair of numbers, which might be called P and Q in the book, they might be called M and N in the book, but whatever we call them, we're going to look for a pair of numbers, and that pair of numbers has to have two properties simultaneously. The first property in that pair of numbers is that they need to multiply together to give me how much? When you were doing your work on this? Negative 18. And that negative 18 came from the constant term in our trinomial. So my pair of numbers, when I multiply them together, have to give me negative 18. Let me pause for just a second and reintroduce a friend from Monday. It was also a friend from last week. Namely, this is our grid method of factorization. So in our grid method, what we're trying to do is we're trying to work, because we're factoring now, from the inside of this grid toward the outside. So we saw an example on Monday where we took the expression that we started with in the problem and we placed it on the inside of the grid. And then the task was to try and work from the inside of that grid toward the outside to figure out what can I place on the outside of this grid such that when I re-multiply it, I get the right expression on the inside of the grid. So that's our goal. And we can start that process by queuing in on the number negative 18 and asking, what are the different ways that I could put two numbers on the outside of this grid? So that would be here and here. And we know that they're numbers because they multiply together and give us a number, negative 18. And so that pair of numbers needs to multiply together to give me the negative 18. But also, thinking about it in this grid method, we can do the same thing with x squared. So let me ask you, what do I multiply together to get x squared? X times x, yeah, exactly. So that part is the same in all of our factoring problems. Anytime we're trying to factor an x squared, we're always going to think about it as an x and an x. Okay? Thinking about it as an x squared and a 1 or something like that is probably not as helpful as we'd like for it to be. Okay, so this pair of numbers has to multiply together to give me negative 18. But that gives us a lot of different possibilities, right? 18 has a lot of different ways that we can factor it into a pair of two factors. But only one of those is actually going to get us to the answer that we're looking for. So what else has to be true about that same pair of numbers? Yeah, it has to add up together to give you how much? Negative 3, the coefficient of the middle term. And so again, thinking about why that is, if I were to multiply out the top row and the top column of my grid over here, then here's where I'm going to borrow the book's lingo for a second. They call one of these numbers out here P. They call the other number out here Q. So maybe this is my P box and this is my Q box. Okay. If we were to reverse this process and multiply, then in this cell right here, I would get P times X. And in the cell down in the lower right, I would get Q times X. And since those are like terms, when I add up everything in my grid, the Px and the Qx are going to add together and going to give me P plus Q times X. X squared plus P plus Q times X, and then minus 18 or whatever. But that P plus Q needs to match up with the minus 3 in our original piece of the problem. Right? So that tells us the criteria for how to find this pair of numbers. The pair has to multiply together to give us negative 18. And by the way, that's the first part that I always think about, is breaking it apart as a product. But then that same pair also has to be a pair that multiplies together to give me negative 3. So what pair was that? If you did this factorization part of the problem, what were your two numbers that you got? 6 and 3. So 6 and 3 multiply together to give me positive 18. So one of those has got to be negative if we're going to use a 6 and a 3. Negative 3. Okay, so now the product is right. 6 times negative 3 is negative 18. But the sum, 6 plus negative 3, is positive 3. So that's not quite what we want. What should we have done here instead? Move the minus over to the 6. Because now the product is negative 18, and the sum, negative 6 plus 3, is negative 3. So now, and by the way, I feel like this process always involves a little measure of guessing and checking. Right? Taking some various paired factors of negative 18 and figuring out which one of those tries gives us the right sum. And here, negative 6 and 3 is the pair that does. And we can check. This is the greatest thing about factoring. Even though it's a really burdensome and creative process, we can always check our answer by multiplying back out. So if I remultiply in this table, the upper right-hand cell is going to be negative 6x. The bottom left is going to be 3x. And if I then combine all those terms back together, x squared minus 6x plus 3x minus 18. Sure enough, when my like terms combine, I get back to x squared minus 3x minus 18, which is where we started, which means that we have a valid factorization. All we need to do is write it in its factored form, which we can do just by writing the two factors that we see on the first row of my table, x minus 6, and on the first column of my table. I don't have a plus in front of here, but I can and should put one, x plus 3. So that's the solution to the first part of this problem. If the problem is to factor the expression x squared minus 3x minus 18, then the answer to that problem is, here's our factorization, x minus 6 minus x plus 3. And we got there both by kind of playing this little game about the sum and the product of our two unknown numbers has to be, respectively, negative 3 and negative 18. But then also kind of organizing our work again using this grid, a little grid mnemonic that shows us what exactly it is that we're doing. We're going from the inside of the grid to the outside and finding a factor of x minus 6 and a factor of x plus 3.